So why should a temperature rise of a few degrees matter? I raised that question earlier, right back in lecture 1. I answered it in several ways, and I'm going to answer it in more detail now. First of all, that rise, remember, is the global average temperature. The global average, averaged over the entire planet, over the Arctic, over the equatorial regions, over the oceans, over land. The rise will be greater by roughly a factor of 2 on all land areas. Not every point on land will go up. Some points will still go down. But on average, the rise in the temperature over land will be bigger than the global temperature rise by roughly, very roughly, perhaps a factor of 2. The polar regions will rise much more dramatically. And from what you learned in the last lecture about the ice albedo feedback, you can kind of see why that's going to occur. In lecture 3, I gave you a number that I wanted you to walk away from this course with, and that was the number that represented the temperature difference between the present temperature, the present interglacial warm spell, and sort of the average temperature at an ice age, and it was on the order of 6 degrees Celsius. So when somebody tells you the global temperature in the next century might go up 4 degrees Celsius or 3 degrees Celsius or whatever, that's not much smaller than the difference between now and an ice age, a difference that meant, again, Northern Europe and North America being covered by a few miles of ice, a couple miles of ice. That's a big climatic difference. So globally, a difference of a few degrees can be huge in terms of the global climate. That's another reason. And finally, a third reason is that if you look at statistical distributions in general, even a small shift in the mean value of some statistically distributed quantity can result in big changes in the extreme values. That's another reason why a few degrees makes a big difference. If you think of something like the grades on a test in a course, or the temperature extremes, or the maximum temperatures you get in a given day, they tend to distribute themselves in a bell curve. There are a lot of values grouping right near the peak of the curve, right near the average. And very few at the tails of the distribution, the extremes that are very far from the average, are very, very unlikely. And that's what makes this bell-shaped distribution. Now, if the average temperature goes up a little bit, for example, a distribution of temperatures moves only slightly. Let's say it goes up a degree or something. The average value goes up a degree, and that whole bell curve moves over only slightly. And that doesn't very much affect things that are happening around the mean. But what it does do is affect much more dramatically what's happening at the edge. And if you work this out mathematically, way out in the tails of that distribution, in the very rare events that are very far from the mean, even a very small shift in the mean value dramatically raises the likelihood of those events. If you've seen my teaching company course, Physics in Your Life, I describe the same phenomenon with respect to food spoilage. Why is it that you can leave a bottle of milk in the refrigerator for 2 weeks and you take it out on the counter and it's spoiled in an hour? In the grand scheme of things, in absolute temperatures, that difference isn't all that much. Why? It's because the extreme events, the high energy molecules in that case that cause the chemical reactions that cause spoilage and the biological activity that causes spoilage are much more enhanced with even a few degrees of temperature increase. And the same is true in climate. Any extreme events that occur in climate, even though they're very unlikely, their likelihood is greatly enhanced by even a slight shift in the mean temperature. So the one thing we should expect, in addition to just the temperature going up, is an increase in extreme, unlikely, but extreme events. One such event is heat waves. I mentioned heat waves before. Heat waves are extreme events where the temperature remains very high for a long time. And I'll just give you a little anecdote from today, because I heard the weather report this morning, and today in the Washington, D.C. area is going to be the 25th day in a row in which the high temperature is above average. Now, if you think about that, on average, the high temperature should be above average half the time and below average roughly half the time. This is 25 straight days in a row in which the high temperature has been above average. That's an extreme kind of event. That's why the meteorologists took note. That's an unusual event. You might get a string of 2 or 3 days, or maybe a week, where the high temperature is above average. That wouldn't be too unusual. But 25 days in a row, there's something unusual about that. That lies way out on the extreme of that bell curve. And it's that kind of event, that kind of extreme, unlikely event, that's enhanced by global climate change, by even a slight change in the mean temperature. You may remember that in the early 2000s, there was a heat wave in Europe that killed tens of thousands of people. Now, you can't attribute any single event, like the 25-day streak I'm just talking about, or that heat wave in Europe, to human-caused global warming. you can't pin down any one event any more than you can say one particular case of cancer was caused by radiation or something. However, analysis of that heat wave in Europe, statistical analysis, says that was so far out on the extreme, so far out on the tail of the bell curve, that there's only a 50% chance that it was caused by natural effects. So there's a 50-50 chance that that heat wave that killed tens of thousands of people in Europe was anthropogenic in origin, caused by anthropogenic climate change. There are plenty of other extreme events that are likely to occur more frequently because of a few degrees change in the average temperature. They include intense precipitation events, they include droughts, they include intense tropical storms. I talked about tropical storms before and showed you a correlation between tropical storm intensity and sea surface temperature. That, like many other aspects of climate, is a little bit subtle and nuanced. For example, we know that warming ocean waters should contribute more energy to make the storms go, and as the warming penetrates deeper into the ocean, the agitation of the storm, which in previous eras would have brought up cool water that might have quenched the storm, will now bring up warm water, and that may make the storms more robust and longer lasting. On the other hand, there are subtle changes in wind pattern, and hurricanes, when they try to form, if there's too much wind shearing along at high altitudes, that will simply shear the top of the hurricane off, and the hurricane won't be able to form. So there are subtle effects here. But we do expect more intense tropical storms. One of the most significant and most talked about aspects of climate change is sea level rise. That's not an easy thing to measure. Sea level itself, you might think, well, there's a uniform sea level all around the world, but that's not true. The sea level varies from place to place. Furthermore, the land areas are going up and down still. One reason they're going up and down is they're still rebounding from the last ice age, when huge blocks of ice weighed the continents down, and when the ice melted, they began to rebound, and that rebound is still going on 10,000 years after the ice melted. So it's difficult to measure sea level. In the past, we used tide gauges to measure sea level, gauges at particular locations that measured the sea level as the tide came in and out. But even their measurements, again, have to be corrected because the land on which they're sitting may itself be moving up and down. More recently, we use measurements from satellites that look down on the ocean and can get measurements over broad areas of the sea surface, so we have a better feel for what's going on. During the last ice age, sea level was 120 meters roughly, that's about 400 feet below what it is now. Sea level changes dramatically with time. You can imagine what that would do to the world's coastal cities if sea level suddenly dropped 400 feet, which it did because all that water was locked up in ice. And the sea level rose quite rapidly as the ice melted, but by about 6,000 years ago, that rate had slowed to about 1/10 of a millimeter per year. That's not very much, 1 to 2/10 of a millimeter per year. Tiny, tiny little rise every year. Today, we see a significantly greater sea level rise of about 10 times that, about 1 to 2 millimeters per year. What causes sea level rise? You probably think, well, it's caused by all that melting ice that I talked about earlier. That's some of the cause, but the most significant cause is simply the thermal expansion of the water. The ocean acts like a giant thermometer. The water expands when it's heated because the molecules get farther apart because it got more energy, and consequently the whole water level rises. And by the way, that's a process that will take some time to complete as the heat penetrates further and further into the ocean. It's only the surface layers that have been affected so far.